Hello, I hope everyone is doing well on this hot day. Today's lecture, we want to talk a bit about TOR anonymous routing and hidden services. And in addition, our TA will also give a few demonstration, one on public key infrastructure, the other is on cross-site scripting. So recap, last time we talked about various kinds of denial of service attacks and the importance of having high availability and making investments, having different replications of your system on geographically dispersed locations. We talked about the importance of TLS, the three phases, handshake, key derivation, the most important part, where the public key verification, the certificate is verified, and then the data transfer using symmetric keys. And we talked about the tunneling, virtual private network, and on the internet, you never know what you are seeing. You may have seen HTTP packets, but then the payload may be some chat protocols, and you may see DNS traffic, because DNS is often allowed on the most restrictive firewalls. The DNS port, I think it's 23. And then there's this concept called DNS tunneling. People package HTTP or FTP, SFTP as the payload of DNS, but they are really not DNS payload, name translation payload. But as long as your server and the client agree upon how to peel off the layers, it can work. And so go back to a TOR onion routing. This is a fascinating topic. You can hide yourself on the internet, and the key idea is to hide yourself among the crowd. Last time we talked about the mixed network. Today we want to say a little bit more about how it works. And here it shows example that you have three proxies. Alice wants to send a message to Bob, and then the threat model is that you will have people analyzing the traffic patterns, and then be able to figure out, oh, Alice is talking to Bob. And so you don't want to directly send to Bob some traffic, and also you may not want Bob, you being Alice, may not want to have Bob know where you are, your IP address. And so the only way, the high level idea is to take a long route. But then the message has to reach Bob and it has to make sense. And so and then also very importantly, no one in the middle, all the proxies should not learn the content. And so how does this work? And you've already learned all the crypto primitives, and so you should be able to figure this out on your own. But I want to just make sure everyone is on the same page. So go back to our whiteboard. And let's just think the simplest example where you have Alice and then one proxy and Bob. And the threat model is that Alice wants to be anonymous and no one knows that they are communicating directly. Okay, so suppose that everyone has their keys set up, a private, public key. And then Alice used one proxy. And so the first step is very, very importantly to encrypt the message for Bob using Bob's public key. And no matter how good this mixed network or onion routing is, it's only to ensure anonymity, its privacy. It says nothing about confidentiality. If you don't want people to see your message, encrypt it with the destination's key. And so let's just call ciphertext for Bob. And then and the next step is to construct the message to send to proxy 1, okay? You cannot just send CB to proxy 1 because proxy 1 will not know where to route it, right? So, and so you have to say, okay, we want this message to Bob, to be delivered to Bob, and so this is concatenation, and then this is, let's call it the message for proxy 1, and then Alice would encrypt the message for proxy 1, M1, with proxy 1's public key. And then this will give the ciphertext for proxy 1. Okay. And of course, this is sent to proxy 1. The step 4 is proxy 1 decrypt with the private key, and only because the private key is kept confidential, only proxy 1 can decrypt it. And this hopefully bring back M1, and then we know that it says okay, this is a message, but then this message has to be delivered to Bob. And so now at this time, after seeing this, proxy 1 knows, okay, we have to send this to Bob. And then step 6, of course, is decryption at the final destination, and this should go back to the original message. So pretty straightforward, very similar to original communication, just with this one proxy. How about with one more proxy? Let's just do 2 proxy. With all the keys you need set up at the beginning. And so the communication goes like this. First step, still the same. End-to-end encryption is very important, and we'll talk about the mistakes people have made. And then the next step, so the next step is interesting, okay? So at this point, you have the ciphertext B. So ciphertext B is to Bob, and so we say, okay, we have to do something like this. And this is intended for proxy 2, right? So this has to be a message that proxy 2 sees. And so it's encrypted using proxy 2's public key. And so we're just thinking backward, okay, thinking backward. And so this has to be on a whole delivered to proxy 2 by proxy 1. Okay, and so proxy 1 sees this, and the proxy 1 need to concatenate further, I'm running out of space, with a message that's to proxy 2. And this has to be chosen by Alice. Alice chooses all the proxies, okay? Chooses all the proxy, knows all the IP address, and then construct this gigantic message. And so the whole thing is this is the message that has to be delivered to proxy 1, and so this whole thing has to be encrypted with the proxy 1's public key. Okay, so if you look at this, Alice has a lot more work to do than last time. She has to, okay, what does she have to do? First construct the message to Bob, okay. Encrypt this with proxy 2's public key, and then concatenate with some instructions for proxy 1, because otherwise proxy 1 would not know where does it go. And then this encrypt Let's see. Right. So let's just call it for message 1 and then encrypt message 1 with proxy 1's public key. Okay, and this is C1. This is a lot more complicated and send this. Let me just use this part. C1. Okay, and then when proxy 1 received it, step 5, of course, is decrypt C1 with the key. This will get M1, and M1 is this whole thing. And so proxy 1 knows, oh, I have to route this big chunk, okay? This big chunk, which is, let's call it M2, which is CB concatenated to Bob, and this is, let's call it C2, okay? So this is, so step 6 is get C2 to proxy 2. And this is the C2. Step 7, decrypt C2 and this will reveal both the message, the ciphertext to Bob, and also the delivery information. Okay, and then Bob, of course, will decrypt the message with Bob's own key. And so you see that every time that there's not only encryption but also delivery information, the IP address, and also Alice will have to prepare this again and again and again, encrypted, wrap it into several layers in like an onion ahead of time, at the beginning of time. And so you can work it out with the 3 proxies, and then it should be very similar. And the concept of this is widely used in TOR onion routing as well, which we'll talk about today. And the major difference in TOR onion routing that instead of using public keys, as in mixed network, TOR onion routing set up TCP-like, TLS-like channels, so that the proxies and all different nodes use symmetric encryption that enable much faster communication. So mixed network would not work for surfing and viewing videos, because it's just slow. But if it's email, less time sensitive, it's fine. The public key would, in general, you would not want to do public keys for time-sensitive web applications. TOR onion routing is a deployable solution. On average per week, so hundreds of thousands of people use it all around the world, and then there are volunteers who offer their computers as relays. And it's very important to know anonymity really is based on having lots of people involved, and so it's sort of a confusion strategy. Otherwise, how can you hide yourself? You cannot. We'll see. In here, there's 6,000 relays, and some have different labels. There's entry relays. Those are the proxies in onion routing, exit relays, and so on. So how does it work? Now we know, this kind of having 3 proxy, choosing them ahead of time, and then wrap the messages around, and so that they would be able to route to the destination. It's similar. And so what Alice does is that be able to query a certain directions, and the direction has all the available relays that can be used. And then this relays, Alice contact to the number 1 relay. This will be the entry node, and then there's also the exit node. And altogether you identify 3 intermediate nodes, and that's typical number that you use for one onion route. And then the route keeps changing over time. Sometimes you can set it to change every 10 minutes. And so that for each connections, it's end-to-end encrypted. But then overall, you will not, attacker not having the complete knowledge of all the relays. And this is very important assumption. So we do not assume attackers control all the relays or the majority of the relays. And so you, each relay will only see traffic coming in and going out, but will not be able to see, okay, this is the final destination, and there's traffic, have the bird's eye view now. And so each connection uses symmetric key encryption to set up. And so the security goal is for Alice not to reveal her IP address, but still be able to send the content to Bob and also receive Bob's responses. And it's very important in this discussion right now is just a regular TOR onion routing. Bob is as a service, the IP address is known. And we're not protecting Bob's anonymity. Bob could be Amazon and so on. Only Alice wants to protect her IP address. And with this onion routing, Bob has no idea where the message comes from. It's, Alice just pass it around, and then the exit node's IP address is the IP address that Bob knows. And then for going back to Alice, same thing. So you use the same route, and the route is updated all the time. And the security analysis, essentially, there's several assumptions for this to work. And it's very important to know the threat model is that attackers will be able to monitor its own nodes, incoming and outgoing traffic, and make correlation and so on. But we assume that for the nodes not controlled by the attackers, those nodes are semi-honest. They follow protocol, but they may try to decrypt and then do correlation analysis. TOR routes in each node, the routes multiple messages, and this is very, very important key assumptions. Otherwise, if you just see Alice, there's only one route, and then you see Alice is sending something to the TOR network, and that must be from Alice. No major corruption and no collusion. However, the one example, the solution that I showed you here has some problems. That is, you have just one route, right? So you have one route, and then you have Alice sending and receiving, participating, interacting with the entry node. And so the attacker would be able to know that Alice start to send some messages, and by eavesdropping on Wi-Fi, maybe on the same Wi-Fi as Alice, maybe at Starbucks, or Alice's neighbor. And in the meantime, attacker may also know that after a few seconds, a few milliseconds, Bob will receive a request. And so, so this could be correlated. And in particular, entry node also knows that Alice starts some communication. And so the problem is that if Alice only use Tor onion networks when she needs it, of course people would be able to guess something, okay? And so the problem is that you would you don't want to show your intention of doing onion routing, okay? If your intention is, if your action is always do onion routing when you need it, when you need to communicate to Bob, then people would be able to infer your activity. And so the solution is have Alice also serve as a node as well, and so is Bob, okay? And in that case, Alice sometimes also relay messages for other people. And so you see that traffic coming out of Alice's machine, going into Alice's machine, and you have no idea which one is for her, which one is just passing her machine through. She's doing it to help other people. And so you cannot follow the communication trail easily now. And because everyone has a whole bunch of messages coming in and going out, and then it's all encrypted as we have shown. It's just sometimes it's symmetric encryption, and so it's just doesn't, you cannot make sense of it. You see some encryption traffic coming in and going out, right? So this is a very, very important. If you use Tor onion routing and if you consider the threat model of traffic analysis, you do have to serve as a Tor nodes as well. So that's basically the onion anonymous routing for the client, where a client can hide her IP address, and server doesn't care. Okay, server would okay, but server does not know the client's IP address. So this is a very, very powerful building block. Very powerful building block. You can have A anonymously route to B without B knowing A's IP address. So assuming that now you know this building block, of what can we do with it? Can we make some extension, do fancy things with it? And one of the fancy structure is called hidden service, called Tor hidden service or Tor service. And this is where the server will also hide its IP address, and then the client can still be able to visit. And it sounds like an oxymoron, because how can you not be able to know where Amazon.com is and then still be able to receive packets and buy stuff? And Paul Sorensen from Naval Research Lab is the onion routing inventor. And so the hidden service, WikiLeaks use hidden service, and it's based on the concept. First of all, what exactly is it for? A lot of times that resist censorship, resist attacks, physical and cyber attacks. If you don't know where the server is, you cannot burn it down. You cannot, set it on fire, and you cannot block it, right? You cannot block the URL, the IP, the domain name. And so, but then the problem is that, this is a paradoxical part of the hidden service. The client need to find it. So how can someone do it? And so we have learned so far is this one-way onion routing, this, asymmetric onion routing, right? So one is anonymous, the server is not anonymous. Now we want to have symmetric anonymity. Both sides are hidden. So how can we do it? Let's think a little bit. How can we do it? So Maybe use the help of third party. Did you think of this? Use a third party. Maybe onion route to the third party, A onion route to X and B onion route to X. And then they somehow like know each other. Sure, yeah. That's actually essentially the basic idea, okay? So you have two separate onion routes, and then you have someone who managed to marry the two routes together. And in this way, NMBR both can stay anonymous. But how does the third party know where to find this server? Yeah, that's a good question, because or in other words, that how does the whole thing starts, right? So the third party must know something about the server. May not know the server's IP address, but certainly has some trust of the server, so that the server would choose to route to it, right? So there's some prior setup, and then we can just publish the third party's IP address. So no one knows the server's IP, and then we want to start communicating with the server anonymously, okay? So let's take a look. Let's take a look to see how this can be done. So the basic idea is to have the server pick the third party, and this is a special third party. And in turn, specifically, there are actually multiple third parties involved. But then for now, let's think that there's, think of this as a server's agent, and then the server ahead of time would onion route to the agent, and then publish the agent's IP address, so the client will be able to onion route to the agent. Okay, and then the agent will will help connect the two routes. And so this is very similar like buying houses, and you have buyer's agent, you have seller's agent, and then the actual buyer and the seller stay anonymous, unless at the final house closing signing they see each other, but they don't have to. So this is the basic idea, and I do encourage you to all read at torproject.org. There's a lot of excellent descriptions, and very importantly, for those of you who use a Skype, Skype use something very, very similar for users behind network address translator. Think of an address, as a lot of the Wi-Fi routers, and the whole local area just have one IP, one real IP, and so all the others they will have to translate. Whenever they send out something, so your computer may not have a real IP, so people cannot call you through Skype from outside. And so one way of doing this is to have, when you fire up your Skype program, it connect to some third party computer where IP is known, and then advertise your availability. Daphne is online, and then at this point other people can call you, and really they call the third party then connect your connection. And so sometimes you will see this kind of traffic going back and forth on all the Skype users' machines, even though you are not making active calls. So the location hidden service, the TOR, a little bit more specific. So we have the server above on the right-hand side. It choose introduction points. Introduction points are the public-facing machines representing the server. Their IP address are published, and there's some directory service that lists the IP address of the representative. Those are agents of Bob. And then you get the service descriptor. there's some sort of directory information, publish all the IP address. And so that when Alice want to visit Bob's server, Alice first will have to look up the directory and then see who are the introduction points of the Bob. Okay, and then so that is the most important step in TOR hidden service. Now you have, you're in business because you're no longer hidden. Bob is no longer hidden. Alice does not directly connect to introduction point, and this is probably for engineering performance related issues, because if introduction point become overloaded, then you may have similar denial of service attack, that they can become a bottleneck. So the protocol requires Alice to choose a rendezvous point of her own and only route to that RP rendezvous point. And so now Alice is no longer hidden. Alice also has a public facing machine that represent her agent. And then Alice send the rendezvous points address and some additional information to introduction points of Bob, and just sort of like an application. Okay, here is my information, my rendezvous point. Do you want to accept my connection? And then Bob would choose if Bob chooses to speak to Alice, after seeing the request, Bob would then connect to the rendezvous point. And this is where both parties, Alice and Bob, the client and server, now have a middle ground. They know each other now through rendezvous point. But very importantly, they still don't see each other directly. They don't know each other's IP address, and nobody knows their IP addresses because it's onion routes. And rendezvous point will massage the traffic and then connect the two circuits together. That's it. Right. So that's it. And so that's why the individual onion route is very powerful. Where we have 3 proxies, and then we use TLS type of connection for each connection, and then the routes keep changing in every once in a while, but then you still be able to communicate. And so that is a very, very powerful building block. And so, you go back home and make sure that you understand that the RP and IP, none of them know where Bob is, or Alice, for that matter. And it's truly a hidden service. Some information, some reading, and TOR has been up here in the news a lot. WikiLeaks, of course, use TOR, and also hackers use TOR. And the WikiLeaks has a lot of serve a lot of purposes. Whistleblowers. So you're afraid of being retaliated, so it's very important to have this kind of service, and so that nobody knows who submitted the documents, and also the server cannot be taken down. Silk Road use TOR hidden service according to the FBI, the DOJ documents, this FBI indictment. How was Silk Road located if they use, right? So if they use TOR hidden service, where are they caught? And this is a massive underground dark web selling illegal drugs and other illegal activities, extremely bad. So first of all, this is for cybersecurity ethics. Don't do evil. It's very important that you use your cybersecurity knowledge to do good things for the society, and because it's easy to do evil things, it's a lot harder to be the good person. Okay, so it's very, very important. I don't teach you to become an evil person, so please don't. And I know you won't. So Silk Road was called because some of the traffic didn't go through TOR, and so they were like FBI undercover agents and noticed there's an IP address with some Silk Road connection, login page, and that's eventually is the point. So some of the misconfiguration caused that problem. TOR, so this reminds me that our Virginia Tech has this Pulse, so VPN, and if you haven't used it, try it. You can specify, do you want to route all VT traffic through VPN or all traffic through VPN? Sometimes I have to use VPN because I need to access certain journals, scientific journals, and then only VT IP addresses are allowed to access those journal articles. And if I'm outside campus, off campus, I have to log on to the VPN first. And so all my traffic routes to a gateway in Virginia Tech with the Virginia Tech IP address. Within the subnet, and therefore from the journal's office, so server's point of view, I'm using a campus machine, and so this is VPN, and it's very, very useful. This is TOR protects A, confidentiality, B, privacy, C, both. Your answer should be B. It's very important to know that TOR by itself does not provide end-to-end encryption. A lot of people fell into that trap. As we mentioned earlier on, when we do mixed network, it's very important you encrypt the message using receiver end's public key or symmetric key or whatever. It has to be encrypted. Otherwise, you are just routing a message through a whole bunch of strangers. Okay, it's actually worse in terms of confidentiality. The exit node will be able to see the message. And so that's exactly what happened back in 2007. Researchers posted email passwords from 100 embassy, government, Fortune 500 companies who use onion routing and thinking that they are to go above and beyond and protecting their information, but turns out they didn't use end-to-end encryption. And it's very important when you write emails, there's no end-to-end encryption unless you add it. What is it? What is the two ends? One end is you, the sender. The other end is your mail recipient. If you send me an email, I'm one end, you're the other end. End-to-end encryption means you have to encrypt your message with my public key or a key that we both share. If you don't do that, there's no end-to-end encryption. That means Google will be able to see our messages. And the Virginia Tech will probably be able to see our messages as well upon what they will be able to see our messages. And Google will be able to say, they usually don't reveal it to authority, but then upon request, and then this is getting more and more easy to send a subpoena, the court subpoena to obtain records of your email, and so it's a lot easier to get your email record. So don't think email is confidential. A lot of people will say, I think as students you don't have to worry too much. And some people say that if you don't want this message to be published in New York Times or Wall Street journals, then don't send it in email. And so that's just how public emails are. Make sure that you do understand end-to-end encryption. What does it mean? Okay, and when we talk about HTTPS, we say it's end-to-end encryption. One end is you, the other end is Amazon.com, Overstock.com, BT.edu, gmail.com. That's the other end. So that's the end of our discussion today. And we'll have an additional demo for you as well to help you do your cross-site scripting programming assignment. All right, that's it. Thank you.